I just started the recorder, and it is recording the right screen. Okay, just basic confirmation. So anyway, it basically showed me, ways to do this, blah blah blah, and blah blah blah, and blah blah blah. So I chose to use the CSV method, and I uploaded, the table. I initially uploaded the entire table, but it's getting confused. So anyway, I had to fix it a few times until it got it. So there we go. Okay, the cleaned file is well organized and appears to describe the table for an instructional processor. And here's the architecture, blah, 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 blah. Okay, so now I go like, okay, let me just describe more details because XX is representing a register, X, and then YY is describing, one of the four registers, Y, blah, blah, and so on. In other words, everything that is in the opcode table spreadsheet was described to ChatGPT at this point. So it confirmed its understanding, like, register A is 00, register B is 11, and so on. And I is representing a constant value, and so on. Flags, RAM, and I also told ChatGPT that we are designating register D as a stack pointer. So at this point, ChatGPT understood the basic instruction set and also how we use the registers. In this case, only register C is special. So right away, I basically told it, okay, to push a value already in a register, say register B, we use the following instruction, and I'm just confirming with ChatGPT and ask, do you understand this? If so, do you understand how to pop a value? So basically I'm assessing, whether ChatGPT 1 understood why those two instructions is going to push the value of register B on the stack, and then I'm also asking whether it can solve a problem. Because at this point, I have not yet presented the code to pop a value from the stack. And I have not even talked about what a stack is. Okay. So um, so this was the first surprise. Okay. I was a little surprised that it was able to explain, what is decrement D and what is STDB, and the explanation is actually correct. So now it figure out, how to do the pop operation. That was never presented. Okay, I never presented the solution to ChatGPT, and it figured it out. Okay, but it's not just that it figured it out. It was able to explain it. So now I confirm that its understanding is correct, and then I said, um, I use the dot notation, okay, because I'm trying to explain, how the dot 6 plus notation works, okay. So I basically said, okay, the dot notation specifies the address of the opcode where the mnemonic is describing. Okay, do you guys have any issues? Oh, you need to plug in? Oh, okay. Yep. If you sit close to the wall, there may be outlets, along the wall. Hmm? Okay. So I'm gonna wait a little bit because when you guys are fuzzing with this, you may not be paying attention. Even though, this is not super duper important, I think it is still kind of important. You just need a USB-C. Uh, there may be outlets on that side. Um, well, I have an extra outlet here, so if you wanna, come sit over here, you'll be able to plug that in. Yeah, so give me the adapter and hold on to the end. When this building was being conceived, okay, when we were working on, what do we want in this building, I specifically said that, bring your own device to your school is going to be something that is going to happen by the time the building was done. And I said, we'll need, basically power strips or, somewhere for each and every student to plug in a charger. Guess what happens? That got totally ignored. I also said the lighting here, anything that's close to a projector, we need something that is more directed so it doesn't splash on the screen and then it washes out the picture on the projector. And guess what happens? It gets totally ignored. Okay. So I think that's a general theme that when I say something, people tend to ignore that. I hope that is not happening in this class. That's just my observation. Anyhow, so I described the dot notation, and ChatGPT was able to sort of figure out, how to work that out. So it basically just, did a whole bunch of things, and this is wrong because it thought we can directly access the program counter. So the pop or the return operation would be specified this way. Um, and that would be incorrect. So I have to basically correct ChatGPT and say there's no PC as a register that can be directly accessed, and the following code sequence is used for calling. And I asked ChatGPT, do you understand these corrections? And it said it was able to understand the corrections. So it's one thing to say I understand the correction. It's another thing to re-explain things to reflect the understanding or the corrected understanding. So this time, ChatGPT was able to figure out, okay, what each instruction is doing, and it is actually correct about that, and also how the six was calculated, why this works, and so on. And then I added, let me present some additional information because now it needs to know how to count the bytes. Okay, and as a result of this addition thing, I asked it, can you explain why the dot six plus works or how it works? And it was able to give me the full explanation how the six happens because the LDI instruction takes 2 bytes, the decrement instruction takes 1 byte, the ST instruction takes 1 byte, and then the JMPI instruction takes 2 bytes. So by the time we get to the halt or whatever instruction is right after the JMPI, it'll be 6 bytes away from where the dot is representing. So anyway, I just share the entire link to all of you, not to basically say that, okay, read this whole thing and you're going to be able to understand everything that we have talked about in this class, but it does illustrate 2 things, okay? And both of those, I think, are important, okay? The first one is how ChatGPT was able to understand, the architecture with basically no prior knowledge that I have, at least not what I have uploaded, about assembly language programming, about how mnemonics are supposed to be used, the syntax of the mnemonic, and so on and so forth. It was basically able to learn from the opcode table itself and figure out, oh, okay, this is the syntax to do certain things. Okay, now it does have some misunderstanding about, like it thought that PC is one of the registers that you can specify in the instructions. But that's reasonable because I never told ChatGPT about the actual architecture that you guys have, the logic file. So it didn't really understand what is inside the processor that the program counter cannot directly be connected to the data port of RAM and be able to read from it. Okay, so there are certain restrictions that we understand because we have the actual circuit, description, and ChatGPT was never presented the same kind of information. But once I make the correction, it was able to go like, oh, okay, in that case, we'll make this work. So the rest of the conversation, which is kind of also interesting, was how it could not understand the dot notation is representing the address of the instruction where the dot is located. So it was doing all kinds of calculations, and they were kind of wrong, but it was able to figure out how to push parameters on the stack. So when I asked it to implement a C function call of XYZ and then 123 as the arguments in assembly code, it was able to figure out all the code. Yeah, what took us, I would say maybe 3 weeks or so, okay, 2 to 3 weeks to talk about in this class. It was able to figure it out. I never told it how to do it. I never presented a sample program of how to do this. It figured it out. So that's kind of that's the first part that is interesting, okay? Because from your perspective, okay, I'll correct myself. From the perspective of your potential employer who's interviewing you, okay, what do you think is relevant in this discussion? Hmm? Problem solving, and it would appear that ChatGPT was able to do at least a certain degree of problem solving. Okay, the second part, the part that I think is the most impressive about your ChatGPT or about this conversation, is the reading comprehension ability of ChatGPT. Now, am I really surprised? The answer is no. Okay, because ChatGPT, along with many other engines, are called LLMs. And what is LLM representing? Large language model. Exactly. Okay, so it has been trained on terabytes, petabytes of information, of text, and extracted the syntax, of or the grammar of natural languages. And I said languages, plural, because if you ask ChatGPT to translate something into different language, it will do like almost a perfect job. Okay, is it like as good as a human can do? No, but it'll be better than most of us. Even for those of us who are bilingual, it will still beat bilingual people. It cannot beat professional interpreters or translators, but it will beat most people. Okay, so I think this is the part where it is kind of important to understand what it can do and what it cannot do. Okay, and how to use it as a tool. Okay, so right here, I was going through a whole conversation, because it kept giving me the wrong result, but it was able to understand what is supposed to be on the stack. Do you remember this picture? I would have, in this class I have presented the same thing but in a different way, but it presented the picture. It's like, okay, the last argument is a top address, and then we have the second argument, the third argument, and then the return address is at the lowest location. So um so one thing, so that's the first part. Okay, let me just kind of recap the first relevant point of this entire discussion is ChatGPT is, even as it is right now, okay, is already capable of this. And you are more than welcome when you have time, okay, to read through this entire conversation just so that you have an understanding of what it can do, okay, how little information I have presented and how it was able to figure out from that piece of information of how to solve certain problems. Was it perfect? No, it has some misunderstanding of some concepts, but when I presented the correction, it was able to figure out, oh, okay, this is where I got it wrong, let me try again. Okay, and it was eventually able to find out the correct solution. And that's when I kind of ran out of time. The commenting is also wrong. I could have just told ChatGPT to use slash slash to start comment instead of a semicolon, because semicolon is the typical way for assembly language programs to start a line of comment. But in this class we use slash slash. So I could have just kind of told ChatGPT about that. So that's the first relevant point. Okay, is to understand what the tool can do, and particularly keep that in mind in the context of after I graduate from here, after I transfer from here, after I get my bachelor's degree in computer science, and when I'm about to find my first job. Okay, what should I do in order for my potential employer to go like, oh, okay, I can see that there's value in hiring you, and I'll offer you a job. But you have to know your competition. Your competition is not just the many people who have lost their jobs at this point, because computer science actually has an unemployment rate of, I cannot remember. That's the sort of thing that you can search for. So, which is, this discussion is not to depress people, but I think facts and information is important. Okay, so you can ask, what is the current unemployment rate of computer science recent graduates? Okay, there we go. It's 7.8%. and it has spiked to 11.7%. Okay, that's pretty high because the national average unemployment rate is about one half of that. So you have to kind of ask the question, okay, if the tech sector is hot, okay, Elon Musk, Sam Altman, all these, and what's his name, the Nvidia CEO, Jensen Huang, okay, all of those people are saying, okay, we need people, okay, we need to hire more people, but at the very same time, we have an unemployment rate of 7.8%, and then a lot of tech companies are continuing to let go of people. So you kind of have to ask why, what is happening? Yes.
I don't um I don't think that 7.8% is actually like competent programmers. I think that the majority of those people just BS their way through college and didn't actually learn
Mm-hmm.
the material, the sectors in the field. So that's why it's growing because everyone thinks that they can become programmers
Mm-hmm.
and get hired, but it's not that easy. Like you have to actually be pretty good. I mean, not to build a Facebook yourself.
Yep. Excellent observation. Okay, excellent observation. So that's a good analysis. But an analysis is needs to be associated with action plan, right? So what are you going to do based on the analysis and the information that I have presented? It's not something that I'm going to answer in today's class, okay? Because that's a really kind of complex kind of thing, to think about. Um, but it is nonetheless, okay, important, okay? So that's the first point, okay? Yeah, it took me about what 20 minutes to make one point. The second point is actually getting back to the same conversation here, which is, can you use this as a tool to help you study so that you become a more competent computer science person, so that you can like what Traders just said, so that you can beat the competition. And remember, your competition is not just people; it is also AI, but it's not today's AI. Okay, because by the time you graduate with a bachelor's degree in computer science, the soonest for most of you is 2 years. Okay, if because if you're graduating right after this semester, it will still take you 2 years to get your bachelor's degree in computer science. So do you think ChatGPT and all the other AI engines will stay exactly the same as today in 2 years? No, because Moore's law is not dead. Okay, so that means every 18 months to 24 months, hardware is going to double in its capabilities. Twice the storage, twice the processing speed, and so on. And that is assuming that we do not even have breakthroughs in terms of how to design chips and new algorithms to solve problems, new ways to basically perform all the neural network computations and so on. Okay, so in 2 years we can expect ChatGPT, um, Gemini, and all the other AI engines to be more capable than they are today. Now there are certain theories about there's going to be a plateau, like there's a cap to how much we can do with this kind of technology. But as you can see, even today, okay, this kind of technology is already doing a fairly good job. So how do you make use of this as a resource? Well, I think I can get the homework assignments done faster if I just kind of copy and paste the question into ChatGPT and copy and paste the answer back. That will save me time. That is not going to help you, okay? Because if you are not going through the process of answering the questions, figuring out the code, and also going over the proof and so on and so forth, you're not exercising your mind, and so that's not going to help. What it is going, the way it's going to help you, at least from my perspective, is there are certain people who write in a way that may be cryptic to the rest of the population. Yes, I am guilty for being that person. Okay, I've been accused multiple times by not just my students, also people who just know me. Okay, my acquaintances, because the way I write is very dense. Okay, information density of my writing is really high. Okay, you have to read something, like 4 times to grasp everything that I meant to convey. But ChatGPT did not have a problem reading that because it's a machine. Okay, its reading comprehension skill is beyond, I would say, 95, 98% of the population. So what you can do is to use that as a mechanism so that when you don't understand, the text of something, it can be calculus, it can be, classes that you'll be taking, as upper division classes after you transfer. So it's not even, not even talking about this class. You can upload the content and then have a conversation with ChatGPT. So you can say, okay, I'm not fully understanding this concept. Can you explain this concept in smaller steps? Okay, can you give me an example of this concept? Now, it doesn't always give you the right answer, okay, because if you follow this conversation, you will find that there are a few places where it did not give me the right answer, but mostly because I forgot to mention about something, and also because it has no awareness of the actual circuitry of the TTP architecture. But in this class, it'll be we as humans have access to the architecture. Um, so you may not be able to 100% trust the reply from ChatGPT, but you can use it as a starting point. In other words, if you're not sure about the answer from ChatGPT, what are you going to do?
Ask you.
Yep, that's right. Ask a human expert. Okay, but you can still use it up to a certain extent. Now, it depends a lot on the subject matter, okay? So if this is a political science class, I would say ChatGPT is going to give you a pretty good answer, okay? You'll probably be correct 95, 98% of the time because it does not involve, hard logic and actual things that are really kind of binary. And when I said binary, I'm not saying 0 and 1. I'm saying it's either correct or incorrect. There's no gray area in between, okay? But if you're talking about political science or psychology and some other classes where it is mostly about linguistics, mostly about understanding the text and not about the application of the hard logic, I think ChatGPT can probably do a really good job, in terms of reading the material and then presenting it to you again. I'll give you yet another example. I have a book, okay, and the book is it's called Cultivating Genius and Equity Framework for Culturally and Historical Responses, literacy. And this book kind of focuses more on literacy, which means you're teaching English literature or history, that sort of subject matter. It does not pertain to STEM. The book does not even claim that, okay, this is how people should teach STEM classes. Okay, so I was able to have a conversation with ChatGPT to ask it, okay, so of the content of this book, how can we apply some of these techniques to teach STEM classes? And was able to answer those questions. Okay, I can see why authors of books are pissed about AI because I don't need to buy that book anymore. I can have a conversation with the book, and the conversation goes beyond what the author already knows. The author doesn't really understand STEM. She's not claiming that, oh, okay, this is how we can apply all of these techniques also to math classes and computer science classes. She made no such claim whatsoever. But ChatGPT, having the background knowledge of just about everything that has been written and published on the web, was able to go like, oh, okay, if you want to apply these techniques to STEM, I can give you some ideas. And it gave me examples, actual concrete examples of what can be done. Yep. But from your perspective, you're not trying to teach a class, right? You can do some research like this and give your professors some suggestions. That may work, okay? But from your side, you can also ask, how can I become a more effective student? What are the more effective way to study classes, okay? To do the homework assignment and so on. So I think this is a very important potential resource for us, for all of us, okay? Professors, students, employers, people who want to be employed, and so on, okay? Um, so that's all I want to say, okay? Keep an eye on this kind of technology, and when you have time, okay, try to experiment with it. You might be surprised of what how it can help you. Okay, the only way that it's not going to help you is if you ask it to for the solution itself, and then all you do is to look at the solution. Okay, but if you ask ChatGPT to help you understand something, to help improve your own competency, I think it is one of the best tools ever because it's not a person, it's not judging. Okay, you can keep asking it questions, and it will just kind of keep answering your questions. If you have a question, if you wake up like 3 a.m. in the morning and go like, I'm really kind of bothered by this thing here. Do you want to call up your professor at 3 a.m. and expect the professor to pick up the phone and have a conversation with you? Okay. Well, okay, computer science professors may still be up by 3 a.m. because they got stuff to do. Okay. But most other professors are not going to reply, right? They won't reply to text because, they're not awake. But you can still have a conversation with Chat GPT, and you can continue an earlier conversation. So everything is saved. If you pay $20 a month, these are all conversations that are saved already. In other words, if I want to continue this long conversation about how to teach a class in STEM and make sure that the content is accessible to everybody, I can do that. 6 months later, I can also continue this conversation. So keep that in mind, okay? All right. So having said all that, let's go back to the kind of more boring stuff that we need to do. How is your homework assignment coming along? There are two programs that you need to write at this point. One is for the swap function, and the other one is for Fibonacci, which is a recursive function. So how are we doing with those programs? Do we have any questions? No questions. Okay. Well, some people do not have questions. I see some people kind of turning their head. But what about the rest of the class? I mean, this is kind of what I would do, for the rest, kind of for the semester. Do you want me to go over more sample programs? Okay, because some people learn better when they see, oh, okay, I see another example of how to do blah blah blah, so they can learn better that way. So would that be helpful? I see a lot of nods. Okay, so I'm going to write a program and which is similar to the program that I wrote yesterday for my Monday, Wednesday class, but this one is slightly different. Okay, so I will go ahead and do this. Okay, so I will say this is a add add to. Okay, all right. So I'm going to write a function that returns. Okay, it's not going to return anything. It's a void function. So we'll say add to, and we'll pound includes std int.h uint underscore t, and this is a pointer. Okay, so the first parameter is a pointer to a unsigned 8-bit integer. So we'll call this p for pointer, and then the second one is of the same type, and it is basically a value, how much to add to whatever p is pointing to. I'll call this k. So what the code needs to do is to say whatever p is pointing to should be increased by the amount specified by k. And then we have int main, and then we have a local variable. Well, let's have two local variables. Okay, so we have uint8 underscore t x, uint8 underscore ty, and then we initialize one of them. We have we have to initialize both. So we'll say x gets a value of 3 to begin with. We say y starts with a value of 5 to begin with, and then we say add to. Um, I want to add to x the value of y, return 0. Okay, so that's the whole program. So can somebody tell me after the function call to add to, what is going to be the value in x? Hmm? 8. Okay, so 8 is the correct answer. Okay, because we're passing the address of 3 to add to. We're also passing the value, not the address, but the value of y, which is 5 sk. So by the time we get to the function, it is going to say, okay, let's start with whatever value p is pointing to at this point. So that would be 3. And then we add the 3 to the 5, and then we store that 8, which is the sum, back to where p is pointing to. So this statement here, which is called a compound assignment operation, can also be seen as this. These two are actually the same. It's just that, oh, okay, take that out. Okay, so these two lines are basically saying exactly the same thing, except one is easier to type, okay, it's a little bit faster. Which one do you want me to use in this class? I can use either one. The first one on line 5 or the second one on line 6. They mean exactly the same thing. The second one, you like the first one? So that we have a kind of discourse here. I'll comment one of them, okay? Just so that we know that they are the same, okay? All right, so when I explain, I'm gonna use line 6 for the explanation because it does spell out the operations into smaller steps better in that way. All right, so we'll do a V split so that the screen splits into two halves like that. And then as usual, on the right-hand side, we'll implement the assembly code. So this is going to be temp. This is add2.ttp.asm. Okay. So we have the usual no op, and then we call main first. So we also need to initialize the stack pointer ldid0, and then we have to push the return address on the stack. Main does not take any arguments, so we have ldia dot 6 plus, and then we have decrement d stda that pushes the return address on the stack, jmpi to main, and then we have a halt instruction so that we basically stop execution after we return from main. And then we'll start with main first, okay? So basically, I want to teach you guys, what is the process of writing programs in this class. So we'll start with main, and then we, define a bunch of labels. Main x is going to be 0 because it is the first local variable. Kind of just by convention, we want x to have a lower address compared to y. Is that a rule? The answer is no. Is that part of the caller-callee agreement? The answer is no, because these are local variables, which means the callee needs to know how to get to them. But the caller says, I don't care about your local variables. You can allocate it from any place. Okay, that's not my business. So that means the locations of x and y can be reversed, but just by convention, this is kind of how I like to do it. So main y is the offset to find local variable y on the stack, and it is 1 byte after x. Okay. Now we have main LVS, which is the local variable size, which is basically combining x and y. How many bytes do I need? So you can just say 2, but I personally prefer to refer to the last local variable and then plus the size of the last local variable. So that's just my preference. Okay, if you turn in code and you just have 0, 1, and 2 as those labels, I'm not going to deduct any points. Okay, it's not a problem. But personally, I prefer to do things this way because I am looking at the relative location of things instead of the absolute location of things. If you want to know, why is it better to just look at the relative location of things and not the absolute location of things? Interestingly, ChatGPT can answer that question. So I'll leave it up to you guys to kind of experiment with, ChatGPT or Gemini or Claude. Those are the three biggest ones, in industry right now. All right. So now we have to reserve, space on the stack. So that means, we have to LDI be with the number of bytes that I need to reserve for the local variables, and subtract that much from the stack pointer. Because when you subtract from the stack pointer, you're allocating space. When you add to the stack pointer, you're deallocating space on the stack. So the way I write code is if I have a beginning that should have an end, I always do the pair at the same time so that I don't forget. And then main is just a normal function. So when the function returns, it needs to do the LDBD um, increment D as JMP B. There we go. So that's the usual return sequence. Um, if you follow the conversation that I showed a little bit earlier, ChatGPT was able to figure out the return sequence. Once I told it that PC is not a register and you have to kind of go through a lot of trouble to use JMPB, it was able to figure that out by itself. I did not even present the solution. So anyway, so right here, okay, this is where we have the local variables already allocated, but not initialized. So now I have to implement line 14 of the C code. And the more systematic way to do it is to make use of these labels here. So this way, if I have additional local variables or if I change the way of the frame, I don't have to worry about a single thing because the labels by themselves are indicating where I can find the local variables. All I need is to go like, oh, this is just the offset. But if I add the stack pointer to the offset, then I get the address. So LDI, you can use any of the three registers at this point. I'm just going to use register A here. Um, so we need X, so add AD. So now register A is the address of X. And I go like, okay, I need to store a 3 to it. So let's put 3 into register B. STB, STA through B is going to finish the operation. So once again, I'm not intentionally missing all the comments here so that you can add the comments, okay? Because of the process of understanding what is going on here and adding the comments is, well, it's one way to study for this class, okay? There are many, many ways to study for this class, just not one of the conventional ways to study for this class. There's no 300-page textbook that you're going to read, okay? All right, and then we can do the same thing with y, which needs to be initialized to a value of 5. So for that, I think, we can recognize the template of code from line 16 to line 19. It's just going to be the same thing, except this time we wanted to do it to local variable y, and the value that we want to use to initialize y is going to be a 5. So the way I would write code, okay, in this class, is you can write code like this, okay, but you need to make sure that the code does work. So that means I'm not comfortable with line 21 to line 24 unless I already know line 16 to line 19 are going to work. So that means that would be the first thing I need to check. Okay. Now, some of us may be very confident about our programming skills, but even the best programmer, okay, make mistakes. Okay, like operational stupid mistakes. I do that all the time. Okay, so that means even if you think that you are a really competent programmer, it doesn't hurt to test the program in stages. Okay, I put a halt instruction here because I want the entire program to stop execution right there on line 21, just so that I can confirm whether I put a value of 3 to where variable x is supposed to be. Is that okay? Okay, so there are really two questions embedded into, are we okay with this? The first question is, do you know what we are doing? The second one is, do you know why we are doing this? Okay, so there are two questions involved. So the first question is, the answer to the first question is, by putting a halt instruction here, the program stops execution, and we should be seeing something happening, and we need to confirm whatever is happening is what we're expecting to happen. That's the first one. The second question, which is why, is I need to make sure that this is all working first, okay? Because writing any additional code at this point is not really going to be helpful if this is not working. So I need to discover problems as early as possible. All right, so now that we have the program here, and I'm going to make sure that I save the file because I'm the kind of person who usually forget about saving a file and then go test the file. So now I'm saving it. And then, oh, this is about the old program. This is the program that we did on Wednesday for my Monday Wednesday class. You are more than welcome to check out that video as well. Okay, if you have the time to do it, I think it's a good idea. But we are covering basically the same material in this class. So now I go to River Spider, 310. Okay, and now we go to temp. I think it's called what again? Add to .ttp-asm. Okay. So when the program is doing this, I got a task to do because I need to show myself what I'm supposed to be seeing on the stack. Okay. So instead of just going to the assembler and go like, oh, okay, let's find out what the program is doing. I need to figure that out first of what I'm expecting the program to have done at this point. Okay, so that part is really important too. It may sound like, oh, that's going to use up a lot of time. It's a waste of my time. No, going through this, mentally and try to figure out what the program should have done is also a form of studying for this class. Okay, so I just really kind of point out, how to study for classes like this because I think that is actually important. So I'm going to make a new spreadsheet with today's date on it. So this way you can actually read it now. Okay, it's okay right there, 2024, 11/21. Okay. So first of all, I'm gonna have some locations here. I'm not gonna be fancy. Okay, I'm just gonna type up F F F E F D F C F B F A. I think that should be enough. Okay, we'll just give it a few more just to be sure. There we go. Oh, F8. There we go. All right. So column A are the addresses. Column B is going to be saying, okay, what is supposed to be there? So what do you think is supposed to go to location FF? What was the first thing that we pushed on the stack, given the program that we have written up to this point? So you have to start from the entry point of the entire program, like from the very top. Okay, we have a no op. No op doesn't do a single thing. We have LDI D0, which is initializing the stack pointer. The very first time we do a decrement, why did we do the decrement? Because we're about to push the return address from main back to the entry point. So that's how this location, which is location FF, should be used for. Okay, so I'm just going to document it. Okay, and you can always kind of make the spreadsheet look a little nicer. Okay, by kind of shrinking a column width to just the minimum, so this way you can fit more stuff on the screen. So this is going to be the return address from main to the entry code, okay, which is the startup code of the entire program. Are we good with this? Okay, then the program proceeds to main, and in main, what is the first thing that we did in main? I'll show you the code and see if you can tell me what we did first in main. So you can focus on things that has to do with the stack pointer, okay? You can see that, okay, line 10 to line 12 actually did not do a single thing at all because all they do is to define labels. Labels are concepts that are useful when we are assembling the program. But the program that is assembled does not have anything corresponding to the labels, at least not directly. So that means the first instruction that we execute is actually on line 13 once we get to main, which is loading the constant of main LVS into register B, and then we subtract that much from register D. So what is main LVS? If you look at how the labels are defined, main X is a 0, main Y is what we would call main X plus 1, and main LVS is main Y plus 1. So what is main LVS? It's 2. Okay, it is just 2. So that means we are subtracting 2 from the stack pointer. Okay, so there are the 3 things. Okay, what are we doing? Why are we doing this? And how it is done. Okay, so at this point, how it is done, which is the internal pathway of the processor to get this done, is not really that important to us anymore. So for the most part, I will only answer the question of what and the why. Okay, so now we know the what. We are subtracting 2 from the stack pointer. So the next question is, why are we doing that? So we are focusing on line 14. Why are we doing this? Yep.
This is all the add to function.
No, this is on your main. It is under the label of main, which means this is all part of main.
What's the main underscore x? That's just the label.
It is the name of a label. So once again, there are those 3 questions. What is it, and why does it exist? Okay. It is the offset of in number of bytes of where I can find local variable x from where the stack pointer points to. That phrase has been used many, many times, okay? But just because every word in the sentence is understood, the sentence itself may not be understood, okay? So that is something that only each one of you as an individual can assess, okay? Is, do I understand that sentence, okay? But that whole thing stems from the fact that the callee, the function being called in this case main, is responsible to allocate for its own local variables, and there are 2 of them. Okay, but I will answer that question with a spreadsheet also, just a little bit later. So can somebody else tell me why we are performing line 14, which is subtracting 2 from the stack pointer? What is the purpose of doing that? Okay, allocate space for the local variable on the stack. Exactly. Okay, so that is something that is important. Okay, because that is a conceptual thing, which means we are doing this because of the structure, because of how a function or a subroutine works. Okay, so we go back to the spreadsheet and go like, okay, so these 2 bytes are allocated for the local variables. Okay, which one is x and which one is y? According to the label definition, which one do you think is x and which one do you think is y? Hmm? That is correct. So this is x of main, this is local variable y of main. So this is the stack pointer, okay? So by the time we get to that instruction, the stack pointer will be pointing here. And now we have a frame, okay? The concept of a frame, can somebody remind me what is a frame in the context of this class? What does it consist of? What is it, and why does it exist? Okay, those 2 annoying questions is coming back. So what is a frame? What is in a frame? And what is the purpose of a frame? Why does it exist? Okay, so first answer the what, and then we'll address the second one, because we can see the what right here. Okay, the what is already presented on the projector. So what is in the frame? The frame has these 3 things. So what is it? What is in it? Mm-hmm. Yep, exactly. So every function call would involve at least one of these 3 items. Okay, the one item that is mandatory is the return address. The other 2 items, or the other 2 groups of items, which are the parameters and the local variables, kind of depends. Okay, you might have some functions that may not have local variables. Okay, that's fine. You may have your functions that may not have parameters. That's fine too. Okay, but if those things do exist, they would be part of the frame. The purpose of a frame is to establish a context from the data perspective of what the function is going to need in order to do its job. So in order for any function to do its job, it needs parameters potentially and local variables potentially. Does that make sense? If somebody says, but I can do everything using global variables, I would say, get out of here. Okay, global variables are bad ideas. Okay, because they can lead to coding, a coding style that makes programs exceedingly difficult to debug. Okay, so if you can avoid the use of global variables in general, avoid them. Okay, if you say, but then all my functions will need like two more parameters to get the job done, then add those two parameters to your functions. Okay, because the whole idea of using global variable is really, really bad. Okay, so there are other ways to get around some of the issues of not using global variables, but avoid them if you can. The only time you will need global variables is when you have a multi-threading program. Okay, so do you think you should be concerned about multi-threading programs at this point? No, because you have not even heard about multi-threading programs until now. Okay, in the context of ARC. So that means all programs that you write really should not have global variables unless your professor specifically say, okay, we are having this global variable with this particular function. All right. Okay. So if I were to store, okay, so I'm going to take out column C right now, and I want column C to be the exact value, okay, I actually can calculate the return address from main to the entry point. So if I go back to my source code here, this is byte 0, byte 1, byte 2, 3, 4, 5, 6, 7, 8. This would be byte 9. So that means I can actually manually calculate that 09 should be the content at location FF. Okay? Then you guys may say, but that's awfully you know, uh, tedious. Okay, if I have to figure out the location of everything by counting like that, that's going to be tedious, and I will easily make mistakes. And you're correct about that. That's why labels exist. That's why we use .6 plus. Okay, because we know the number of bytes between the LDI instruction and the halt instruction in this case is going to be 6, as long as we keep that template of code. So once we have those kind of patterns, we can go like, oh, okay, we don't have to do all the hand calculation at this point. But right now, both of these locations have unknown content because I have not put anything into those yet. Are we still doing okay so far? All right. So now we switch back to the code here, and then we are now on line 16. Line 16 is putting a main X into register A. Main X is defined to be 0. Well, that's an easy one. So that means register A is 0. And then we add the stack pointer to register A, and register is a 0. So that means register A is the same as the stack pointer. So that means at this point, register D points to this location. So does register A. Are we doing okay so far? Okay. So at this point, then I put a 3 into register B, and then I store the content of register B into where register A is pointing to. So that means at that point, this unknown location is going to change to a 3. And then we have the halt instruction. So that means at this point, that's what the stack should look like. Location FF should have a value of 09. Location FD should have a value of 03. Location FE can be anything, okay? It is 00, okay? That's because when you power up the machine, it zeroes out all the content of RAM, okay? But technically speaking, from our perspective, we really don't know what it is going to be. And we also know that register D should be FD because it points to the last location that we allocated, and register A should also be FD because it is pointing to the location of local variable X in main. Then what about register B? Okay, register B has a value of 3 because that's what we use to do the copying. Register C is the one that I really don't know because we never used register C up to this point. Okay, so I can summarize the entire state of the processor at this point, and then what do? This is just my understanding. I am the emulator emulating the execution of the program. But not only am I mechanically emulating the processor, it's just going like, okay, if I blindly go through these instructions, this is what's going to happen. I am also explaining to myself and relating those operations to concepts in C and C++. Local variables. Well, that concept does not exist in assembly language programming. It is a C++ concept. Functions. It is also a concept of C++. Calling and returning, those are concepts in C++, not in assembly language. Is that okay? So I'm actually going through a lot of stuff just by going through these few instructions. I'm double checking my understanding of the instructions. I am making connections between the assembly code and the C code. Okay. I'm also relating how we get things done in assembly to implement certain things that we have to do in C++. So I'm doing all of the above. And that's why it took us, what, half an hour just to get through these few lines of code. So now it is time to actually run the code. Okay, so I need to go back to my assembler. So this is all in the actual assembler, which means if you go to the assembler at the end of this class, you can just make a snapshot of it. Okay, so this way it kind of saves you the trouble of having to run it through your own refer spider. So let me go back and run this code. I think I just did, but I'll double check. Yeah, I just did it, but I just run it again. Okay, so now that we have it run, we go to the assembler and then we go to the analysis tab. The analysis tab is the tab that shows you blow by blow, okay, instruction by instruction, what happened. So the no op instruction alignment doesn't do a single thing. That's kind of what we expected. LDI D0, puts a 0 into register D to initialize our stack pointer. Okay, good. LDIA.6 plus is putting 9 into register A because as we kind of calculated earlier, right, the return address to the halt instruction is 09. Okay, that's one confirmation. And then we push the 9 on the stack, so, which consists of decrementing D. So D is now pointing to location FF and then do the store. So this is the first confirmation that location FF has a value of 09. Yes?
Why is dot 6 plus 9? Like, why is LDI? Why is 9 being loaded into register A? How is it being loaded into?
Because the dot is the address of the LDI instruction, which is a 03, and then dot 6 plus means adding 6, so 3 plus 6 is 9.
So column A is the address.
Yes,
Do we actually have to care about that? Like, is that something we should pay attention to?
we just did. I just used it to answer your question. Now, how you use the columns is entirely up to you. But I can say that the column exists in this tab here, in this table here, for a reason. Okay? But I just use column A to answer your question. In other words, I also answer your question of whether that column actually is important.
What about B? Like,
Column B? Column B is not typically very useful, okay? But it is useful if you need to say, oh, I cannot remember what is the content at a certain location. That can remind you, okay, of which location we are reading and what is at that location. Column C is super duper important, okay, because that's how we confirm that right now, okay, 09 is stored at location FF. Does that match our expectation? Yep, right there.
what is FF?
It is hexadecimal number. It is
So
the same.
are we expected to know all
Yes.
of these decimals by heart by this point?
You can do the conversion. We talked about how hexadecimal converts to binary, and we also talked about how binary converts to decimal. So you can go through binary to do the conversion, but you can also go directly because we know that in hexadecimal, the digits run from 0 to F, okay? And because it's base 16, so we can figure out, okay, so let's go through a very quick exercise of 3b, okay? What is the value represented by 3b as a hexadecimal number? 0x is just a notation to emphasize that we are looking at a hexadecimal number. It's a base 16 number, which means this digit tells me how many ones we have. This digit tells me how many 16s we have.
You have to divide it by 16, right?
Huh?
You have to divide the number by 16.
Nope, there's no division involved. B itself is representing what? Okay, let's do some counting here. Okay, we got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But then we have A and then B. Okay, so B is representing what? 11. That's correct. So now we have 11 times 1 plus this 3 is telling us how many 16s we have. So we have 16 times 3, or to be consistent, I'll flip the order. So we have 3 times 16. So that would be 11 plus what? 48, which is 59. So 3B is what we know as 59 in base 10, and this one is hexadecimal. It's I'm just reapplying what we have learned in base conversion. So this is going all the way back to base conversion. Are we good with these concepts? Okay. So yeah. Anyway, so I gotta focus on this one because otherwise we won't be done with this. Right. Okay. So we are done all the way up to this point. Okay, we know this is all working. So this template of code is reapplied to local variable y, so the y ends up with a value of 5. So now we can implement the third and last statement that is of any consequence, which is calling add to with y and the address of x. So this one is kind of interesting. Okay, so I'm gonna illustrate it. The first thing we need to push is what? So on line 16, what is the first thing we need to push? We need to push y first, okay? So, that means, I can do a little shortcut here. I can say LDAA, decrement D, and STDA. They go like, what? Why didn't we do this? What is in register A? What is in register A? The address of Y, exactly. So that means, when you are reading code in assembly, when you're reading my code, you need to track what is in each register. Okay, it's not super difficult. It's just that you have to add comments to do it. Okay, because if I don't use comments myself, like a few like 30 seconds after I write some code, I would have forgotten what is in the register. And then I have to go back and refigure out what is in the register. So at this point, this is kind of like a shortcut to push Y on the stack. Then we go back and say, okay, now we have to push the address of X on the stack. We had the address of X, over here on line 19, but then after that we overwrote register A, so we don't have the address of X anymore. So I'm gonna have to recompute the address of X. I'm not gonna do the shortcut thing of, well, let's use register C over here so that we can reuse register C over here. Okay, so I'm not gonna do the shortcut here. So we'll go ahead and recompute the address of uh, local variable X, which is kind of the same deal as before, like this. If you notice that I have made a mistake, don't say a single thing, okay? Because I want that mistake to persist so that I can show you what that mistake is, okay? Because it is a very important thing for us to understand and to understand how to fix that mistake, okay? So don't say a single word, okay? If you know that there's something wrong with this code, don't say anything yet, okay? Just keep it to yourself. All right. So since we're only pushing the address of X on the stack, I don't need a dereference anymore because register A has the address of X at this point. So I just need to push it on the stack. So we got decrement D, STDA, and then I can push the return address, which is LDI A.6 plus decrement D, STDA. Then I can go to the sum function, which is add to, which is not defined yet. And then when it returns, I'm just going to finish up the caller code first, increment D, because I have two arguments or 2 bytes of arguments still sitting on the stack. When the function is done, why do you still want your arguments to be on the stack? There's no reason why they should be on the stack. So that's why I'm undoing, I'm deallocating the arguments on the stack. So now I go back and start with add to, okay? There are quite a few things I need to do, but I'm not going to do a single thing because I want to know what is on the stack. Okay, because once again, If what is already on the stack is wrong, what I will continue to do to implement add to is pointless. Is that okay? So this is one theme that I'm trying to repeat a few times in today's lecture, which is do it in steps. Okay, you can write the whole program all at once, but you can only debug it a few lines at a time. Okay, and when you debug your program, you kind of have to figure out what I'm supposed to be seeing. Okay, so if I were to go back to my mental simulation, okay, so this is the next location where I push the value of y. So the value of y is, oh, okay, got a few more things to do. Y is supposed to get a value of 0, 5, and that is pushed first. So this location should have a value of 0, 5. And then this location is the address of x, which is supposed to be fd, okay? And then we have the return address, and this time I cannot do the hand counting. I mean, I can, but it's problematic. Okay, how many people want to watch me do the hand counting? Nobody. Okay. Okay, so I'm just gonna say this is going to be the return address from add to back to main. Okay, but I do want to kind of clarify, because if I just say return address, then the question is returning from where to where. So at this way, it is pretty clear. Okay, this is in order for me to return from add to main, this is the address to return to. So that is the current state. Okay, and that's going to be some value, but I'm too lazy to figure it out by hand. And this is where the stack pointer should point to. Okay, so is that okay? Does everybody understand, why the stack should look like this at this point? Does that mean it's going to be like this when I ran the code? That seemed to make sense. The answer is no, okay? I intentionally made a mistake and not fix it, okay? So that we can see the problem. So now we are going to run the code, okay? Which means I have to remember to save it first and then run the code. Okay, there we go. I'm one of those people who wish my programs do not work so that I can actually show you guys and explain the process of debugging a program, because that thought process is actually very important. Okay. But I did make a mistake here. Okay, so you look at all of this stuff here. Okay, so the trace just got a little bit longer. Okay, we store 0, 9. Okay, that's all good. We store 0, 3. It's good. 0, 5. That's all good. So now we can kind of go do a quick confirmation. FE has a value of 0, 5. FD has a value of 0, 3. Okay, all good so far. And then we push the 0, 5 on the stack, which means FC should get a value of 0, 5. Okay, we confirmed that as well over here. And then we are supposed to push the, whoops, sorry. We are supposed to push the FD on the stack too. You go like, whoa, hold on a second here. This is supposed to be FD, okay? And how come it is FC, okay? Because because I because the stack pointer is now one more than what it used to be, okay? So when you see something like this, okay, I'm expecting this to happen, but if something else is happening, what are you going to do? Okay, once again, I'll give you a few choices. One, which is what some UC Davis student would do, is to make some random changes to the program and hope that one of those random changes will fix the problem. I can almost guarantee you that that approach does not work. Okay, it will make things worse in a very unimaginable way. Okay, so what do we do? The whole reason why we have this trace is you can walk backwards. Okay, if you know the problem is here, walk backwards until you find the source of the problem. Is that okay? Now, this is a technique that won't work in regular C++ programming, because a C++ debugger, as good as GDB is, it does not track everything up to a certain point unless you tell it to. Okay, but since we do have that capability, then we ask, why are we storing FC to FB? The location is correct, the value is wrong. So that means whatever is register A in register A is not what we think it should be. Okay, so now we have to track down what did I do to register A. Okay, register A got a 0, 0, and then I add the stack pointer. Then it becomes FC, but I'm still supposed to be expecting this to be FD. It is one short. Okay, so why is it one short of what it is supposed to be? The reason has to do with we decrement D already a little bit earlier. So we can see how, when we push the 5 on the stack, um, okay, I need to, when we push the 5 on the stack, the second 5 at location FC, the stack pointer is now at FC, okay? But okay, I have to go back to the source code here. All of these constants that we define here was based on a single assumption, that the stack pointer is pointing at the base of the frame. Okay, so let's go back to the picture of what the frame looks like and where the stack pointer is, where's the base of the frame and where's the stack pointer. The frame of um, main are these bytes. So these three, okay, I'm gonna use color coding here. Where's my color thing? Dot dot dot. There we go. Fill. We'll choose this yucky color. Okay, there we go. So these 3 bytes are supposed to be the frame of main, which means if I look at the base of the frame of main, which is the reference point from which we calculate the offsets of all the items, I'm just going to put it in column E here. This is the base of main's frame. Okay, so let me make sure that that line of comment is understood first. Are we okay with that thing? Okay, the frame is where the local variables, the return address, and all the parameters are. So do we all agree that location FD is the base of the frame for main as a function? Okay, the offsets in order to access all the items in this frame is based on the assumption that, oh, this is the base. So after we push the 0, 5 here, the stack pointer is no longer pointing at the base of the frame. So that means all the offsets, like main underscore x, main underscore y, they are now one off from where they should be. Does that make sense? Because if you calculate from the base of the frame is where x is supposed to be. But the stack pointer, because we have already pushed y on the stack, the stack pointer is now pointing to one location below the base of that frame, which means, oh, so all those numbers that we calculated earlier, they are now all wrong. But they're wrong in a very simple way because they're just 1 byte off. So that means to fix this problem in the code, what we can do is to say, oh, just add 1 to this. So the 1 plus is to account for the 1 additional push. Okay, when we push the value of x on the stack. Oh, that's not the right place. Sorry about that. This place here. This is the place where we have to compensate for that 1 extra byte that we pushed on the stack because we pushed the value of y already. So the stack pointer is correct. It's not like the stack pointer is wrong. It is correct, but it is no longer pointing at the base of the frame anymore, where the assumption was made when we calculated all the offsets. So all we have to do now is to say, okay, fine, the stack pointer is no longer pointing to the base of the frame. How many bytes are we off? Do we know that? We say, yeah, we kind of know that, because we put the decrement D right here on line 30, right? So we know that we are only 1 byte off. So we say, okay, fine, we'll just kind of add that 1 more byte or add that 1 to when we calculate the address of x, because the stack pointer is pointing to 1 location below where the frame is supposed to start. Are we doing okay so far with that concept? This is really, really important for your recursive function. This one is not important for the swap function, but for the recursive function, it is very important. Okay, so you have to kind of keep this in mind when you work on that one. Okay, so given that we have 2 minutes left, okay, I am going to finish this program. So I don't really have to rush because we have the entire lab. But I don't know how you guys want to use the lab. Do you want to see me finish the program and with all the explanation? Or do you want to kind of do your own thing and ask questions during the lab? Hmm? Finish it? Okay. So do we have a general agreement that you want me to finish the program? Okay. So let's go ahead and finish the program. And I think, just by me explaining this program, especially when I get to add to, it will help you out with both programs that you need to write. So I think that's actually a good use of our time. Do you guys want to take a 10-minute break before we continue? I can do this all day, like 5 days a week, you know. But if you guys need a short break, we can take a short break and come back at 10:30. How does that sound? Oh, good. Okay. So I'm going to pause the recording because otherwise you have like 10 minutes of dead time in the recording. So I will pause the recording, which means I probably need someone to remind me to resume the recording. Okay. There we go. All right. So I'm recording again. I hope you guys got a little kind of short break so that you guys are ready to. Okay. Right. So now we do the correction. Okay, so the correction that we were making was the +1 that I put over here. Okay, so even though it is a very obvious fix to a problem that I have already diagnosed, okay, it should fix the problem, but you know that's a famous last word, okay, or famous last phrase or famous last sentence is it should fix the problem. Okay, so don't make that mistake. And one of the reasons why you have, River Spider is it is easier for you to run the program again so that you can double check and verify that, okay, I think we fixed the problem. Let's just double check and make sure that we did fix the problem. So I'm just rerunning the whole thing and, just go to the same place and make sure that FD is pushed on the stack because FD is the address of X, not FC. Okay. So the program is now done. I go back to the analysis tab, and now we go like, okay, what did we push on the stack? Aha, FD got pushed on the stack, and then we have the return address also pushed on the stack. So now I compare this picture with what I expect to find on the stack at this point. So FA is the return address, which we saw from the other slide. But more importantly, this is supposed to be parameter x of add to. Oh, the other way around. This is supposed to be y because we push y first. There we go. Sorry about that. And did I call those y? No, this is k. And this is supposed to be p of add 2. There we go. All right, so once again, now we have the whole thing reconciled. In other words, what I expect to be on the stack by dry running this code, it's mostly just dry running based on the C code too, okay? To come up with this picture here, I don't need to understand TTP ASM at all. I just need to understand how the stack is supposed to be utilized. What is the stack? What is the stack pointer? What is the caller callee agreement? From all of those, basically, just ways of getting things done, I should be able to come up with this picture. I should not even need to understand assembly language programming, you know, a bit, to come up with this uh, map here. Is that okay? So that's by itself is also some kind of instruction because when people think about programming, they want to think in the language that they're supposed to use to write the programs. So when you have a programming assignment in, let's say, CISP 400 or 360, you're trying to think in C++. When you're trying to do a homework assignment in this class, you may be trying to think in TTP ASM. But the answer is you don't have to do that. You have to think about what needs to be done first, okay, regardless of the language to express that, okay. Because if you try to think in C++ or if you try to think in TTP ASM, you may be distracted by the syntax. Okay, am I supposed to put a semicolon here or over here? Okay, or am I supposed to put parentheses around this register or around that other register? So you might have that. Those are distracting thoughts. But instead, if you focus on, oh, we need to push arguments like this, and then the return address like this. So these locations should be used this way, and so on and so forth. Then you are not having those distractions of how to express it. Okay, so that's just one of the things that I notice when I write programs is I focus on what needs to be done first. How to express it comes later. Is that okay? All right. So now we have another frame. Okay, so these 3 bytes is now another frame. So I'm gonna color code it a little bit just so that we can visually differentiate it from the first frame. So this is now the base of the of add2's frame. Okay, so add2 also has a frame. It also has only 3 bytes because it has the return address and the 2 bytes that we need for the parameters. It has no local variables. Your swap function, on the other hand, has 2 bytes of parameters and 1 byte of local variable. So it's kind of like a mix of these two, okay? But the way we access the parameters and also the local variables are essentially the same, okay? So now let's go ahead and switch gear and talk about the implementation of add2. So I'm switching back to the source code, and now our focus is, how do we do this, okay? All right, so now, just to preserve the ordering of the functions, I'm going to switch to add2 over here. So my way of doing things is always starting with the labels, okay? So because I want to designate what is supposed to be where. So add2 underscore p, okay, I'm going to start with LVS, okay? You go like, but Tag, there are no local variables here. Yes, you're correct. There are no local variables in add2, but I can still define LVS. So if I have no local variables, what would be the local variable size? It'll be 0, okay? That's fine, okay? And people might say, but that's just stupid, okay? If you don't have any local variables, why do you care about LVS? I'll show you why. Okay, so from that, how do I define where I can find the first parameter, which is p, okay? So where do I find p? What is the offset to find p? How does that relate to LVS? Hmm? Say that one more time, please. 1 byte above that. That is correct, because LVS turns out to be the offset of where we can find the return address. But I don't really want to mess around with my return address in the function, okay? And I can also show you what happens when you do, okay, but not in today's class. So now I can say, oh, okay, this is add2 LVS 1 plus, because LVS itself is actually the offset to find the return address. But I don't want the return address. I want the 1 byte above the return address, which is going to be my first parameter. And then the second parameter is right after this. So k is add2p1 plus. So you have to be careful not to switch to infix notation because the assembler does not catch those mistakes. So if I were to say, add to p plus 1, the assembler would actually just make it, add to p, and it won't do the addition and it won't report an error. Okay, so just kind of keep that in mind. I will try to fix that problem, but I really kind of do not want to mess around with the assembler in the middle of a semester because in the process of fixing one problem, I might introduce another problem. It is actually IBM who said, for every problem that we solve, the number of problems that we introduce can be greater than or equal to 1. Okay, think about that sentence a little bit. On the average, when you fix a problem, you'll be introducing, let's just say 1.1 problem, which means the number of problems would only increase over time. Okay, so the ratio of fixing versus introducing new problems, you want that to be less than 1, as small as possible, but it is a non-zero number for sure. Anyway, so now we have all the labels, and the first thing we need to do over here. So when you look at an expression like this on either line 5 or line 6, now the question is, how do I convert that into assembly code? Okay, don't think in assembly code. Okay, think about what you need to do. So when we look at line 6, okay, we'll just say line 6 here. So I can basically go, okay, before we do that, I can put in all the usual entry code and exit code. So the entry code still needs to allocate for the local variables. And you guys go like, but there are no local variables. It would be stupid to do that. Well, yes, it is not exactly useful to do it, but it wouldn't be wrong to do it. In other words, if I were to do something like this, you go like, yeah, but that's just subtracting 0 from the stack pointer. It doesn't end up doing anything. You are correct about that. But if later on I actually want to introduce local variables, this code doesn't need to change anymore. Okay, so I'm always doing this, and there's one term to refer to these things. It's called future proofing your code. So you can look up that term. I did not invent that phrase. It's called future proofing. Okay, techniques that can help you future proof a design is usually a good idea, because that means um, you know when you do need to make some modifications later on, it would not be as involved as without future proofing the code first. And having this kind of bracket way of writing code, which means when I write the beginning of something, knowing that it must have a matching end to it, and I put in both at the same time, is also a technique to quote unquote future proof the code. Because with me, at least, okay, with ADHD, it is unlikely that I will remember to close, to end the code. So then the program will just kind of not finish correctly. Can I detect and fix those problems? Yes, but it will be time wasted. By doing this, I don't have to worry about that anymore. Okay, so it is all about knowing your typical, why sometimes things don't work out for you, and then you have to kind of engineer a structured solution around it, so that way you don't, can you don't have to deal with that as much. Yes, yes, thank you. But thank you for the reminder. It is running again. Yep. All right. So getting back to this. Okay. So now I'm ready to actually write the code. Okay, because I have the whole context already set up. So now the question is, how do I approach this? Okay, how do I look at this one statement here on line 6 and know what I need to do? So this part is about sequencing. It's about the ordering of doing things. So how do you figure out the ordering of doing things? Well, you might want to say, well, what things are we dealing with here? Okay, so I'll just in random order. Okay, you specify things that we need. I think we kind of need those too. Yes, because they are explicitly called for in the C code. Okay, and I also need to perform some operations like assignment and addition. Is that okay? Now, that's probably the wrong order, but I'm just kind of you know putting all the things here so that I can visualize and go like, okay, these are the things that I need to do. How do I do these things? Okay. So in order to get to what P points to, what do I need first? I probably need to get to P first, right? Okay. K is already a parameter. Okay. All right. So we'll just kind of leave it like this. So I'm going to reorder things a little bit. The what P points to I cannot get that until I get to P. And the assignment is one of the last things that I do because I need to perform the addition first. Is that okay? All right, so the order is going like, okay, I need to get to P, then I can get to what P points to, which is one of the things that I need for addition. But I also need to get to K before I can actually perform the addition. Is that making any sense? Okay. So now we go like, okay, but from the assembly language perspective, um, do I have P defined here? The answer is no. Okay, then you guys will be asking, well, if we don't have P defined as one of the labels, then what is add to underscore P? add to underscore p is the offset from the base of a frame to where I can find p. It is just an offset. Okay, so that means by itself, that label, which I have immediate access to, is not the address of P, let alone the actual value of P. So that means, okay, so that means in order to get to P, I need to get to first the offset of P from the base of the frame, okay? And then I have to, from that, I will calculate the address of P, which is, I'm just going to use, the ampersand symbol here. Same thing for K, okay? So I need to, so from here on, I'm just going to shortcut the whole thing and say offset to K. Is that okay? Instead of, repeating offset to K from the base of the frame, I'm just going to shortcut the whole thing to offset to K. Is that going to be okay? All right, okay. So from the offset to K, I will compute the address of K. And then from the address of K, I can finally get to K itself, the value of K. Okay, so now I have a sequence of things that I need, and in this particular order too, because I cannot get to the address of P until I know what is the offset, but I cannot get to the value of P until I have the address of P. I cannot get to what P points to until I have P. Is that okay? So I have my own term to describe this way of thinking. I just call that dependency based thinking. You figure out what depends on what else. Okay? Because when people ask me, I don't know how to get things started. You can start at any point. All you need to do is to say, in order to do this, I need those. So that means the first thing that you mentioned cannot start first. You have to have all the dependencies met before you do the first thing that I mentioned. Is that making any sense? So from that perspective, postfix makes a lot of sense because postfix basically says don't do the addition until you know what you're adding. It makes perfect sense, right? So this is basically just a really long postfix notation of I need this, then this, then this, then this. And then on top of that, I need this, this, this. And once I get to this and this, I can now do the addition, but I cannot do the assignment yet, okay? Because in order to do the assignment, I will need this again, okay? I need this again before I can perform the addition because I need to use P to tell me where I'm going to store the value of the right-hand side of the assignment. Is that okay? So I have never taught this class in this particular way, by the way. Okay, it's just occurred to me today. So a lot of times I have these kind of ideas that just kind of the best way to describe it is it just kind of bubbles up in my mind, and there's a very short amount of time before I capture that, and it bursts, and then it will be gone forever. Okay, so that's why note taking is important. Okay, you guys all have these moments, the eureka moments. Okay, the question is, did you capture those moments and what you come up with as an idea because you wrote it down? Okay, so that's important. And since this lecture is recorded, that's my quote unquote note taking method, right? Note to self, watch this video again. I hate watching my own videos, but sometimes I have to. Okay. All right. So now that we know the ordering of doing things, okay, before I move on to actually implement the code, are you guys understanding the process itself? Okay, dependency based thinking. Okay, you look at in order to do this. So okay, the focus of dependency based thinking is not even to ask the how question. You're only asking the what question. You're asking, in order to do this, what do I need? Not why I need it, nor how do I use it. You're just saying, okay, to do this, I'll need those. Those are easier questions to answer. Worry about the why and the how later on. Just focus on the what. Is that okay? All right. So now we go like, okay, how do we get to the offset of P from the base of the frame? Well, that's the whole purpose of these labels. So we start with those. Okay, we stash it into a register first. Okay, so add to P, stash it into a register, and you. It also helps to kind of indicate what is in register A. So this is my notation, which may not be the notation that you want to use, because this is the address of P minus. Um, there are a few ways to do this. I'm just going to say the address of the entire frame. Is that okay? Yes? Okay. Then I'm going to add AD, okay? Because at this point, I don't have anything else pushed on the stack, which means the stack pointer is pointing at the base of the frame, which is also called the address of the frame. So that means, at this point, A is the address of P. So that's why I'm going to put it over here, because I'm just kind of following my own order that I figured out a little bit earlier. Okay, from that, I need to get to P. So can you guys tell me how I can get to the value of P once I have the address of P already in register A? LDA in parenthesis A, okay? So to get to that instruction, you have to think about what do I need to do? I need to dereference, okay? Then you have to think about, but how do I do it, okay? So once again, what do I need to do and how do I do it? So what I need to do is to dereference. How do I do it? Is the LDAA instruction. There are only two instructions of the entire instruction set that is capable of dereferencing. One is ST, but it's only good for changing the location in RAM. The other one is LD, which is good for reading a location in RAM. So now the question is, are we reading or writing? We are reading. Okay, reading plus dereference means LD is the only choice. Okay, so that's how you can find the answer to that question, is to say, okay, so now we know it is LDAA like that. And once I have P in register A, how do I get to the content that P is pointing to? So let me ask that question again. We have already put parameter P into register A. So let me add the comment here. So you should probably add the same comment to all the programs that I have written up to this point, okay? And you say, but that's going to be a lot of work. Yep, that's kind of how we study in this class, okay? So once we get to this point, we have register A being parameter P, but I need the content it points to. So how do I do it? Another LDAA. Now, can you use other registers? The answer is yes. Okay, so until you find a reason to use another register, we'll just keep using register A. Okay. All right. So now we have register A being the RAM content that it points to, which means nice. I got one of the things that I'm supposed to add. Cool. So now we have to figure out the other one, which is kind of the same thing. Kind of. Okay, not exactly. I cannot use register A anymore because register A now has one of the two values that I need to add. So I cannot overwrite it, or I prefer not to overwrite it, okay? But I do have two more registers to play with, so that's fine. So now I say this is add to underscore K. So I'm going to use the same notation. B is now the address of K minus the address of the frame. Add BD. B is now the address of K. LDBB. B is now K itself. Is that okay? So I'm going to copy and paste a little bit, okay, because this is the offset. And, oh, yeah, this is the address. And this is the actual value of K. All right. So at this point, I go like, I think I got everything I need to perform the add operation. Do you guys agree? Okay. So now I just have to figure out how do I add two things together? There's only one candidate, okay? It's the add instruction itself. So at this point, you can add BA or add AB. It really doesn't matter, okay? You just have to remember which register has the result. So I just I just chose register A, but you can easily choose register B. It really wouldn't matter either way. So now A is whatever P points to, which is in register A itself, plus whatever K has, which is in register B. So I'm using the parentheses to remind myself, oh, okay, but which register has which one? I'm just double checking to myself and go like, okay, these are the two registers that has the components that I need for the adding. Okay, cool. So now the question is, how do I do the store? Okay, the store means, I have now computed the right-hand side. The last thing we need to do with the assignment operation is to, let's update whatever the left-hand side is specifying. Okay, so what is the left-hand side specifying? I need to store this back to where P is pointing to. Okay, so at this point here, I'm not going to do any optimization. So I'm just going to go through the entire exercise that we went through earlier, which is to get to P, I first need to get to the address of P, but to get to the address of P, I first need to get to the offset of P. So I'm just going to go through this whole exercise again, just so that we're getting more familiar with it. Okay. I can now, okay, which two registers can I use at this point without messing up what I need to do? B and C, very good. Because the purpose of register B ends on line 32. Okay, it just has to specify what other value I need to do for the addition. Register A is storing the sum of the operations, so it is still important, but register B has no use at this point. So register C and register B are both usable in this case. So I'm just going to use register B. So to repeat the process, I need to get to the offset first. So that would be LDI B add 2 underscore P. To get to the address of that, I need to add BD. And to get to P itself, I need to do LD BB. Now, I can do this really quickly, because I already know the context. But from your perspective, don't try to memorize this as a template without understanding why it works and how it works. Okay, because in the final exam, I will present sequences of code that can get things done in a different way. In other words, in this class, I might be using a very fixed template to get a certain thing done, but I will explain why
All right, so now it is recording using the computer's own mic. It is still fine, but I have no idea how much of the audio I have lost. Okay, I do apologize for that because I didn't expect this thing to run out of juice so quickly. Mm. Anyway, we are almost done here too. All right, so now that we have P in register B, do I have everything that I need, or do I need to use LDBB one more time? Okay, so you have to think about what is in register B. Register B has parameter P in it. And what do we need to do? We need to store to wherever P is pointing to. Okay, so we know there's a dereference somewhere. The question is, do I need another LD to do the dereference? The answer is, well, what happens when you do use the LD instruction to do the dereference? You'll be reading from where P is pointing to. Are we interested in knowing what content is pointed to by P at this point? No. What do we want to do? Overwrite it, right? We want to store to that location. So that means, at this point, you have to remember to use the ST instruction to do the quote-unquote dereferencing. And the result is actually in register A at this point. So I'm using STBA to store the sum, which was previously calculated on line 32, to where B is pointing to, because register B is now parameter P. So I think that should do it, okay? And I have just broken one of the rules that I said a little bit earlier, which is don't finish, like tens of lines of code before you test it, okay? So, well, what do you guys want to do? Do you want me to just run this code and see if it works? Or do you want me to put in, kind of sprinkle halt instructions until we are confirming that every single little step is done? That's up to you. I can go either way. All right, we'll just run the whole thing. Okay, right, we can do that. So, running the whole thing first is also works because we have a full trace. Okay, now when you're implementing the recursive function, you can end up in an infinite loop. Okay, so in that case, okay, if your program is going in an infinite loop, it is eventually trashing itself and dying. Okay, then you might want to consider sprinkling your halt instructions so that you can at least stop the program at a certain point and go like, okay, what is happening up to this point? Okay, so these are just little tips that I want to share with you guys in terms of how to make use of the tools that are given to you. If my memory serves, most professors teaching 360, 400, and even 430 do not talk about debugging programs. Is that still correct? Knowing how to debug programs or knowing the techniques to debug programs, not only in the context, the really, really limited context of this class, is actually very important. Okay, I cannot make a new class just to talk about it. Okay, so right. So I need to look at the code here, and fortunately this program is not working. Yes, I got my wish. Because what I need to happen here is this location should be changed to 08. That did not happen. Because when I look at the assembly code, is that the right location? Nope, it is location, that's the FD. Okay, location FD is supposed to be updated to, okay, that did not happen. All right. So if that did not happen, the question is, what did I actually store with the ST instruction? And there's no ST instruction here. I think I just pulled another tag, which is forgetting to save the file first. But I thought I did. Oh, then I forgot to run it after I saved the file. But knowing my own, flaws is important. because then I know where to look. When things are not working, I go like, okay, let's check that first because I tend to have I have a tendency of forgetting to do certain things. Okay, so let's see if this is better. Nope, it is not any better. Oh, it is better. Okay, so 8 is actually stored to that location. And then after that, we deallocate the local variables, which is there's none to talk about. And then we go through the usual return sequence of instructions. We get back to main, and main does not have anything else to do because add to is a void function, which means there's no return value to make use of. And then main itself is deallocating its own local variable, which it has two, and that's why the stack pointer changed from FD to FF. And then after that, the only thing sitting on the stack is the return address, which is retrieved by line 86. And then we pop, we increment D to deallocate that location, and then continue execution where B is pointing to, which is on line 7, our halt instruction. So that concludes the entire run of the program. So I did not get my wish. The program did not break. Yep.
You're too good at programming.
Hmm?
You're too good at programming.
Well, it is my own architecture to begin with, and I have worked with compilers since 1990. So from 1990 to 98, it was my professional responsibility to not only to maintain and bug fix a compiler, but also to add new features to the language that the compiler has to compile. So all of this is.
The year I was born.
Hmm?
Like that's the year I was born. 90.
Yes, that is how old I am. All right, so let's take a step back. Okay, I know you guys are anxious to go. If you want to go, that's fine. Okay, I don't have a problem with that. Do we have any questions? Okay, and when I ask, do we have any questions, I'm not only asking about the technical stuff that we have just talked about, the technique of accessing a parameter or local variable. I'm also asking, do we have any questions about the approach of how to write programs in this class? Yes?
When you write a function in assembly, the local variables go after the return address, right?
Okay, yes. Well, okay. First of all, define after.
So on the stack, usually you load like your parameters. Like, say you're creating a function on the stack. Usually, and hopefully I'm right, but usually you load the variables on the stack before you load the return address. Once you allocate space for them. So say I have like.
Oh, okay. Let me reparse that sentence. Okay. Could you say that again?
So on the stack, usually you would load the variables, the parameters on the stack first, like the variables.
I push the parameters first.
Or push them. So
yes.
you have 5 and 3, you're gonna push those into the stack,
yes.
and then you'll push the return address, right?
Yes.
To create your function, essentially, right?
So that's the caller's responsibility. So that's on the caller side.
Yeah.
Okay, continue.
And then after that, if you have local variables within that caller,
The callee.
The callee.
The function being called is the one responsible to reserve the space for its own local variables.
So in order to load the local variables in that function, after the return address, you would push it into the stack, right? After the return address, after you jump into that function.
Okay, so let's think about the ordering of things, okay? The caller needs to do things first, because otherwise, who's calling, right? So the caller says, okay, if I have any arguments to call this function, I'll push those arguments in the reverse order, meaning last argument pushed first.
Yeah, that's
okay.
what I'm trying to get at. Is
yes.
That when you first, like, basically you're building your function in reverse, right? Like, if you have parameters, you're gonna load those parameters first before you load.
Push.
Sorry.
From the caller's perspective, you have the arguments pushed first.
Okay, so you push your parameters first. You push
arguments.
Your
Okay.
arguments.
Yes, you have the arguments pushed from the caller's perspective first. Then what is pushed?
Okay, your return address.
Then the return address.
And then if you want to utilize local variables, then you push those after the return address, right?
The callee, the function will push quote-unquote reserve space on the stack for its own local variables. Yes.
So does that mean you have to jump into that function first, like JNPI?
Yes, it is the function that is responsible to reserve for its own local variables.
So after jumping in, you specify the local variable.
Yes, and that is actually demonstrated in this program because main is just a normal function in many ways. So you can see how in main, at the entry point of main, that's what these two instructions are for. Lines 53 and line 54 is how a function, in this case main, reserves space on the stack for its own local variable and therefore completing the frame.
So you're loading, so main Mr. ODS is just some label, right? You just created.
It is
onto the
not
stack.
just some label. That label is created so that I can calculate the number of bytes that I need for all the local variables. Nothing about this program is trivial. In other words, there is no just.
Yeah.
Okay?
Well,
Everyone,
my question is, you have, so you, where are you declaring main underscore x in this? Is that on line 50?
line 50 defines main. So every time you see a name that is kind of like an identifier in C, followed immediately by a colon, you're defining a main.
So that's, so you're defining the offset of that as 0, right?
Yes.
And then you're incrementing that plus 1,
Mm-hmm.
and you're making y equals to that offset of 1.
Yes, because that's where you're going to find y. The offset of y is 1 more than the offset to x. And that part can be visualized in this particular spreadsheet. This is x, this is y, this is the return address of main. Back to its own column.
So I have it right there that it's all reversed on the stack. So basically, if you're writing code into the stack, you're supposed to write it, or in your words, you're supposed to push it in reverse.
Okay, so let's just look at these 3 items, okay? And then you tell me how we push or reserve space. In what order do we do
So we have y and x as local, or just variables, right? Those are
that?
local
Local
variables.
variables of main.
We push y first because it's the last thing pushed in, so it's going
Wait, but there are 3 things, right? There are 3 things in what I've selected here.
Yeah.
So, what about the return address? Who's the
return-
in what order?
So the return address is first.
Yes, it is pushed first.
Because we're looking at this function, and then y is next.
So y and x are reserved at the same time. Because we are not pushing y, we are not pushing x. All we are doing is to say, okay, together, we need 2 bytes for all the local variables. And both of those bytes, both of those locations are allocated at the same time. So that's done by these 2 instructions. So line 53 and line 54 together is saying, okay, let's move the stack pointer 2 bytes below where it is pointing to right now, because I'm gonna need those 2 bytes for my local variable. So it's not a push, because push implies you know what value should go to those locations while you're pushing. I'm not pushing anything, I'm simply saying, I'm gonna need these 2 locations, I'm just reserving those 2 locations.
I was just like struggling with that offset thing, and I finally figured it out.
Mm-hmm.
So
Very good.
yeah.
And can I answer Antoine's question? Yeah, go ahead.
So all the options are just pretty much reserving space for the return address to local variable.
So the return address is not quote-unquote reserved, because that is actually pushed. It is actually pushed because by the time we reserve that location, we also know what value should go to that location. So the return address of main, okay, so the return address of main, which is this byte here, is pushed from the entry code all the way up here. So technically, lines 4 and 5 are the push instruction, and then line 3 is determining what values it should be. It's determining the actual return address, but the real push operation is referencing lines 4 and 5. All right. So is this part of the lab helpful?
Yeah.
Okay, excellent. Yep.
Just I think the bottom of your
So
code
that's
where
what
you
push
did like
is
SC something.
Uh-huh.
You store, I don't understand that part.
You mean this one? That's in main. You mean you mean this one?
Yeah.
What about it?
So your dereference key is still A and
Yeah, I'm still,
You wanna start up?
build up knowledge.
no. I just, yeah, because we're trying to
Like
do
that part, I don't know how to read.
the dereference of P, which is
I
equal
mean,
to,
FF is 15.
oh, sorry. We're trying to do the dereference of P is equal to dereference.
Because that's FF is
ST stores. It stores to whatever, in this case, on line 40, it stores it stores the value of register A to where register B is.
Can you
It's gonna go all the way to the last one.
I can upload it.
The last one.
and
Well, secret is like watching. Yeah,
I did, I just don't know if it's right. It's kind of guessing.
I think with the so if it's zero zero reduction, that means it's like going all the way back to the last part of those. Only if you can see it into this, like you know what it says. Yeah. Because
I
this
mean,
goes
the
up to
thing-
like
the
15
thing
point
is, we have the values. Last time I did it with Tuck, I got the values.
Because that's
All right. Well, I just uploaded the
so that's like
sample program for today.